Our first hands-on practice with ANNs for classification problems will deal with soil sealing in Wuppertal, a city in western Germany. For this, we will use satellite data coming from the European Sentinel-2 satellite as input data, or X-data as we will call it in our Python script later. As we want to extract artificial surfaces from this satellite scene, we will use soil sealing data as our target data, or Y data as we called it. You see that the soil sealing data is a binary representation whether a pixel is sealed or not. Considering that the whole image we are currently looking at has more than 1.7 million pixels, we should reduce the number of pixels for the sake of computing time. Those red rectangles indicate the regions we will concentrate on. The larger rectangle indicates our training region and the smaller one the testing region. Again, the testing region will not be used during training and only be used to test the performance of our model later. Just as a reminder, when programming the model, we usually call the input data set for training xtrain and the corresponding target data for the training phase ytrain. During testing, the input data is referred to as xtest and the target data as ytest. While there is not a lot of interesting stuff about the binary target data, we should definitely look into the input data. What you are currently looking at is a color composite of the Sentinel-2 scene consisting of 3 channels. But actually, there are way more channels in this dataset, as the Sentinel-2 satellite captures information from several segments of the electromagnetic spectrum. In our case, we will use 10 of the satellite's 12 channels. The fact that we have 10 channels means that we do not only have 1 measurement per pixel position, but we actually have 10 measurements. So what we are going to do in this hands-on lesson is to make a pixel-based classification with the help of an artificial neural network, to take those 10 measurements and predict whether the pixel is artificially sealed or not. And of course, we are not only going to do that for this specific pixel, but for all pixels in our dataset. So let's go to our programming environment. First, we should take care of some imports. I will start with those needed for preprocessing, and as you already know NumPy and matplotlib, I already added them. Since our data is saved as TIFF files this time, we need a module that is able to open them. You will see that the Pillow library is often used to open image data. The problem, however, is that Pillow is not able to open a TIFF with 10 channels. Therefore, we will use the TIFF file library, which is capable of doing this. So we import TIFF file as TIFF. As soon as the imports are done, we can load the data. We start with xtrain and use tiff.emread to open it. The data is in the subfolder data /soil sealing /xtrain.tiff. A hint on the side. There is the .tiff ending with 1 or 2 f's. It is best to check the file's properties to see which one is used to avoid problems when loading. Let me quickly repeat the step to load ytrain, xtest and ytest as well. Next, we should take a look at their shapes. And I will use a simple fprint statement to do that. And repeat this step again for the other datasets. You see that the training region has got a size of 450 by 484 pixels, and the testing area is a bit smaller with 290 by 296 pixels. While the X data has got its 10 channels, the binary target data only has a single channel. That's why it is currently not even listed. The next step is very important when working with geographic raster data. Most raster datasets have a very specific no data value. This might be -999 or any other value. In any case, you should check your data's metadata and eventually set it to np.nan and remove it from your dataset. You can set the no data value to np.nan with np.where and setting up a query to filter for your specific no data value. As I am very sure that there are no data values in our dataset, I will speed this up and just paste this part to the notebook so you can see how this code could look like. You see that everything is fine in this case and we do not have to worry about removing NaN values. Nevertheless, we have a different though small problem. If we looked at our data in GIS, we could see that the unsealed areas have the value 1 and sealed areas the value 0. Even though this would not be a problem for the neural network itself, it is still appropriate to invert the values according to the research question about sealed areas. But first, let us check the amount of pixels belonging to each class with the help of a little print statement. We can use np.unique, provide our y-train data, and set the return counts to true. Then we repeat this for the y-test data. You see that currently about 99,000 pixels have the value 0 and 118,000 pixels the value 1. Let's invert this. We override the y-train variable and use np.where. First the condition again. If a pixel in y-train is 0, then set it to 1, else set it to 0. Then we print the result again and repeat the process with y-test. Now the values are inverted and 118,000 unsealed pixels have the value 0 and 99,000 sealed pixels have the value 1. The last step of our preprocessing is reshaping. Currently our data has 3 dimensions, which we can see within our first print statement we did at the very top. We have width times height times the number of channels for our input data. A simple artificial neural network, however, does not understand the dimensionality of raster data. It only understands 2-dimensional data, meaning one observation at a time with a certain amount of features per observation. So we override xtrain with a reshaped version of itself. So xtrain.reshape, use the automatic dimension calculation for the first dimension, which is just a -1, followed by the number of channels. To make it less hard-coded, we get this information from the second index of xtrain.shape. For y-train, we only have to flatten the image dimension, meaning turning it into an array with the size width times height. We can do this with y-train.reshape and only provide a -1 again to make NumPy figuring out the dimension by itself. Now let us do this for x-test and y-test as well and print the final shapes once again. Now we can finally start with the neural network itself. First, we need some imports. As we have already talked about all the imports that we need, I will just copy them and not go into detail here. The normalization of the input data is nothing new as well, so let us just write it down. We choose a variable name and call an instance of normalization. And adapt this instance to our xtrain data. Then we set up our model as a sequential model. And add the normalization layer. Then I will use a first dense layer with 64 neurons. A ReLU activation function, and provide the input shape based on the X-train shape at index 1, meaning 10 features in this case. Before I add another dense layer, I will deploy a dropout layer as discussed in the previous lesson of this chapter. The number that I'm providing here means that 10% of the outputs will be set to 0 and thus do not signal any information to the next layer. The next layer should then be again a dense layer with, let's say, 128 neurons. And again, a ReLU activation function. Then another dropout layer. And a final dense layer, which only has a single neuron. Now you can pause the video here to think about the final activation function. I would suggest to take a sigmoid, as it scales the output between 0 and 1, which you can interpret as the probability of a sealed pixel. A prediction close to 1 indicates that the pixel the model is looking at is sealed, and a value close to 0 indicates that it is really unlikely that the pixel is sealed, meaning it is unsealed. Next, we need to set up our optimizer, and we'll use keras.optimizers.sgd once again, with a learning rate of 0.01. Then we compile the model. The optimizer is set up the same way as the last times, but this time we will use a different loss function. As we have a classification problem, it doesn't make any sense to use the mean squared error. Instead, we use the binary cross entropy. This is a typical loss function for a binary classification problem. This time, I would also like to get some additional metrics during training. For a classification problem, it makes sense to track the accuracy, meaning the percentage of correctly classified pixels. We can implement this with the metrics argument and provide the metrics we want to see as a list. In our case, we just want to see the accuracy. Remember that the way I call the binary cross entropy or the accuracy is nothing that I defined. These are fixed expressions that must be taken from the Keras documentation. Now let us train the model and track its learning history again with the history variable. We call fit on our model, provide X-train and Y-train, set the number of epochs to only 8, as we will have quite a lot of training data points, and give it a batch size of 256. The training itself might take some seconds or even minutes depending on your machine. In my case, the model reaches an accuracy of roughly 92%. You can also see that the loss constantly decreased while the accuracy improved over the epochs. In case you're wondering why you receive slightly different values, remember that the weights are initiated randomly, so you might have had more or less luck with your initial weights. Let us test whether a different optimizer might reach a better result. I will exchange SGD by Adam and leave all the other settings as they are. In my case, I receive a slightly better accuracy under Adam. But that does not mean that Adam is better for this specific model. Let me show you that if I change the learning rate to 0.1 and run the model again, The results are not better than under stochastic gradient descent. Quite the opposite, in fact. If I use stochastic gradient descent under the learning rate of 0.1, then my model performs actually better. You see that the performance depends on all the hyperparameters that we choose, and changing a single parameter is actually not enough. Nevertheless, we should neither take the training accuracy nor the loss as a single reason to set specific parameters. In the end, the performance on test data is crucial, so let us go on with programming the rest of the script. As we have done the plotting of the history several times now, I will just copy it. The only things that I have changed are the added graph of the accuracy and the legend. Now we come to the validation of our model. To get the loss and accuracy for the test data as quickly and easily as possible, we can take our model, call .evaluate, and enter our X test and Y test data into it. In my case, I get an accuracy of just above 90%, which is okay for now. Just as the last time, I want to extract single data points and see if the model's prediction matches with a true class. I set up a variable called observation that can hold an integer, and use the number provided there to extract the real class of the observation with that index. Then I would also like to see what I actually put into the model for this observation. So I extract the input features from xtest. The 27th pixel is a non-sealed pixel in my case. And those are the corresponding input features from which the model should now predict whether it is a sealed pixel or not. To do that, we say model.predict, provide xtest, extract the observation, and reshape it to the shape that the model needs. And as the output of the model is very close to 0, it indicates that the pixel is not sealed, which, as we know, is true. When I exchange the observation by an index of 14, I select a sealed pixel, and the model predicts a value close to 1, as it suggests that the pixel is sealed. Now, predicting single pixels does not really provide a lot of benefit. Rather, we should generate a spatially extensive dataset on soil sealing, which provides real added value for runoff models, for example. Generating such an extensive dataset for the test area needs exactly 3 lines of code. First, we set a variable which will hold the prediction for the whole test dataset, followed by model.predict for x test data. The problem is that currently our prediction does not have the dimensions of an image. You remember that we have flattened the spatial component of width and height, so we have to reshape this prediction back to an image format. For this, it is necessary to get the same width and height as the original test dataset. I will just look it up in the print statement at the beginning and see that the image had 290 times 296 pixels. With those values in our minds, we take the prediction and reshape it back to the image dimensions. Now that we have back the shape of the image, we can write it to our hard drive with tiff.emWrite, provide a suitable name, for example, probability map.tiff, and provide the data that we want to write into that file, which will be ytestpred. I would now like to encourage you to play around with the architecture of the model as well as the hyperparameters. Add a dense layer, change the number of neurons, play around with the optimizers and their learning rate, and maybe try some more epochs to get used to it. Let us now switch to a GIS to check the results. I already loaded the prediction map from our model as well as the ground truth data. Considering that this is our first ANN for classification, we can be happy with the results. We also could turn this probability map to a binary map by setting a threshold of 0.5 and would then have a binary representation of the predicted soil sealing. The only drawback that we currently have is that our data lacks a geographical reference. This is something you would have to implement in your post-processing. Usually I use the rust.io library to take care about that issue. Then you would replace the parts where we use the functions from TIFF file by rust.io functions.